First of all, I want to give a very brief introduction to machine learning. I believe all of you are already familiar with the basic idea of machine learning, but I have to introduce it a little bit to make sure everyone is on the same page. So what is machine learning? Everyone knows that machine learning is looking for a function. Like if you want to build a dog and cat classifier, that you need is to find a function which can take an image as input, and output is the object in the image. To achieve that, we need 3 steps. So to find the function, there are 3 steps in machine learning. The first step is decide what is learnable. For example, in deep learning, you have a deep network, and the input of the network is an image, and the output is the classification result. And in this network, the network architecture is predefined, or the links between the neurons are already defined by a human, and the weights and biases of neurons are learnable. We use theta to represent the learnable parameters. In machine learning, a function f is denoted as f theta. The function f is the parameter by theta, and this theta is learnable. This theta is learned from data. The second step is, you have to define your loss function. You need a loss function, which is L of theta here, to determine a parameter theta is good or not. In typical supervised learning, you usually define your loss function in this way. You have some training examples. Here you have a set of images of cats and dogs, and you also have the labels of those images. If you want to know how good a set of parameters theta is, and the function of theta will take the image as input and output the distribution, then you compare the difference between the output of the function and the ground truth. Usually you use cross-entropy as the definition of the difference. After you compute the difference between the output of the function and the ground truth, you know how good a function is. You will sum up the cross-entropy of all the examples. Then you obtain the loss function, L of theta. And L of theta is what you're going to optimize in the next step. In the third step of machine learning is optimization. What you have to do is solve an optimization problem. In the second step, you already defined your loss function L of theta based on your training data. Then in the third step, what you need to do is find a set of parameters theta which can minimize the loss function L of theta. A parameter which can minimize the value of loss function L of theta is denoted as theta hat here. And in deep learning, you usually use gradient descent to solve this optimization problem. Then after you have theta hat, then f theta hat. This function is what you find. This function is what you found by machine learning, and you can use this function in classification. So this is machine learning. And I know this is something you have already known the first day you learn machine learning. And so I think you already feel very bored. So let's quickly move to meta-learning. So what is meta-learning? So machine learning can be simplified in this way. So you can consider machine learning as we have a set of training examples. So if you want to build a dog and cat classifier, you collect lots of training examples with their labels. Then you have a learning algorithm. The learning algorithm takes the training example as input, and with some very smart learning algorithms, you obtain a classifier. You obtain a function, which is your classifier. Then the classifier takes an image as input, and output the classification result. And actually, we can consider our learning algorithm also as a function. We use capital F to represent this function. Capital F is our learning algorithm. This capital F takes training example as input, and output the function we desire. Output the classifier we want to find. So learning algorithm can be considered as a function. As you know, machine learning can find the function automatically. So usually we say, after we have the machine learning algorithm, then we can automatically find the classifier from the data. However, the learning algorithm itself, although it is a function, The learning algorithm itself is handcrafted. It is not learned from the data. Some smart people design the learning algorithm, so we can use the learning algorithm to find the classifier. If the learning algorithm is a function, can we automatically learn this function from some training data? This is what meta-learning wants to do. And because meta-learning is also looking for a function, the procedure of meta-learning is very similar to typical machine learning. I spent a lot of time introduce machine learning and say there are 3 steps in machine learning. To do meta-learning, all we have to do is following the same 3 steps in machine learning. Step 1, what we have to do is decide what is learnable in our function. So now the function we consider is capital F, a learning algorithm. So we have to decide what is learnable in our learning algorithm. For example, in deep learning, there are lots of components. For example, you have to design network architecture. Then you have to initialize the parameter of your network. Then you have to select an optimizer to solve the optimization problem. In typical deep learning, those components are handcrafted. Those components are decided by humans. But now in meta-learning, we are going to learn some of the components. Some of the components will be automatically found by machine, instead of defined by humans. So here the learnable components are denoted as phi. So phi is our learnable component. So we denote the learning algorithm F as F phi. Capital F phi means that in this learning algorithm, capital F phi is learned from the data. Different meta-learning techniques make different components in the learning algorithm learnable. This is step 1. Decide what is learnable. For example, you can learn network architecture. You can learn initial parameters. You can learn your optimizer. So in the second step is we have to define a loss function. For a learning algorithm, we have to define a loss function for the components in the learning algorithm, which is going to be learnable. So we have a loss function, L of phi. So this is a loss function for the learning algorithm. If a set of parameter phi obtains more loss function, means it's a good algorithm. If phi obtains a larger loss function, means we have a poor learning algorithm. Then how can we define the loss function? Capital L here? Remember that in machine learning, we have to collect some training data. In meta-learning, what we have to collect is not training data. Instead, what we have to collect is training tasks. For example, if you want to build a dog and cat classifier, which is a binary classification problem, you have to collect lots of binary classification tasks. For example, your training task 1 is to classify apple and orange. And your training task 2 is to classify car and bike. And in each task, you have some training data, and you have some testing data. So in each task, you have some training examples, some testing examples, some training examples, some testing examples. And both the examples in the training set and the testing set are already labeled. We already know the labels of the images. In meta-learning, we have a set of training tasks. Then how can we define the loss function, capital L, based on these training tasks? So given phi or given f phi, a learning algorithm. This learning algorithm can take the training examples of a task as input and output a classifier. This classifier is denoted as f theta hat 1 here. Theta hat 1 is the parameter of the classifier. Theta hat, the hat means this is the parameter learned by f phi. And 1 here means it is learned from the training examples of task 1. So given a phi and given the training example of a task, we can have a classifier, f theta hat 1. If this classifier is good, then that means we have a good learning algorithm. So this learning algorithm should have a smaller capital L. On the other hand, if this classifier performs badly, then that means Our learning algorithm is not good. So it cannot find a good classifier. So this learning algorithm should be assigned larger capital L. So this is the basic idea of how we define this capital L. However, how can we know a classifier is good or not? The answer is very simple. Just evaluate the classifier on the testing set. So remember that in each task, we not only have the training example, we also have testing examples. So we take the image from the testing example and use the classifier, which is learned from the training example, to obtain the classification result. Then we compare the classification result of the learned classifier with the ground truth. Remember that in our testing example, we also have the label, so the ground truth of each image is already known. So we can compare the difference between the output of the classifier and the ground truth. Then based on the difference, we have a loss, which is L1 here, represent the loss of task 1. To be more specific, we have the testing example here, and we have the ground truth. And F theta hat 1, the classifier, learns from the training data with phi. We have the classification result. Then we can compute the difference between the classification result and the ground truth. Then we sum over the difference and have the difference of the whole task. We have L1 for task 1. If a classifier has a smaller L1, means this classifier is good. So we have a good learning algorithm. On the other hand, if the loss is very big, means the difference between the output of the classifier and the ground truth is large, then we have a poor classifier. Then we have a bad learning algorithm. And besides task 1, we have a set of training tasks. So from test 1, we compute L1 for the learn, to know how good the learning algorithm is. Then for task 2, we also have the training example of task 2, and based on the learning algorithm we also learn a classifier F theta hat 2. And we can also evaluate the goodness of this classifier by the training example of task 2. So we have another loss, L2. So L1 represents how good the classifier we learned in task 1. L2 represents how good the classifier we learned in task 2. So now we have L1 and L2. And for all the tasks, we will compute a small l for each task. Then our total loss for a learning algorithm is capital L, which is the summation of L1, L2, the L for all the tasks. This capital L can be formulated in a more general form, like this summation over all the small l, and each L corresponding to a task. And the capital N here means the number of training tasks we have. In this example, we only have 2 tasks, so capital N is 2. But in a real application of meta-learning, you probably have tens of thousands of training tasks, so you can define a loss very well. So this is step 2. So you can find that how we compute a loss in machine learning and meta-learning is very similar. But there is a very subtle difference. In typical machine learning, we compute the loss on the training example. But in meta-learning, we compute the loss on the testing example of a training task. You may feel very surprised, because in all the machine learning courses, you always learn that we cannot use testing examples during the training. So how could you use testing examples here? However, it is okay to use those testing examples, because testing examples are in the training tasks. In the training tasks, we have testing examples. I know this sounds very confused. This is probably how you feel. But hopefully, after we finish all of this tutorial, you will be clear about what is meta-learning. Let's move to step 3. So now we already define the loss function. We already define capital L. So you have an optimization problem like this. You want to find phi, which can minimize capital L. And phi hat is the component that can minimize capital L. Then the next problem is, how can we solve this optimization problem? And this is to disentangle. With the meta-learning technique, just use the optimization approach you know. If L of phi is differentiable, you know how to compute partial phi, partial L of phi. Then if you know how to compute this term, you can use gradient descent to solve this optimization problem. On the other hand, if L of phi is not differentiable, so we cannot use gradient descent, there is another optimization approach. For example, you can use reinforcement learning or an evolutionary algorithm. Now let's assume you successfully solve this optimization problem. You obtain phi hat, which can minimize capital L. Then now, we have a learned learning algorithm. This sounds funny. We have a learned learning algorithm, f phi hat. So f phi hat is the learned learning algorithm. So this is the whole framework of meta-learning. We have some training tasks. And based on the training tasks, we can find a learned learning algorithm, f phi hat here. Then we have a testing task. In the testing task, we have some training examples and testing examples. The training examples in the testing task are also labeled. And this f phi hat, the learned learning algorithm, will take the training example in the testing task as input and output a classifier. So theta hat is learned from phi hat. We have this learning algorithm. We have the training example. So with the learning algorithm and the training example, we can learn a classifier. You can use this classifier to do the testing. In the testing task, we have some testing examples without labels. Then this function, this classifier, can obtain the classification results for us. And testing task is what we care about, is the problem we want to solve. And the training task is not necessarily related to the testing task. Hopefully, with lots of training tasks, which is not related to the testing task, we can find a good learning algorithm. And this good learning algorithm can be applied to the testing task. And hopefully, the learned learning algorithm is so powerful that probably on the testing task, we only need little labeled training data to obtain the result. This is why you usually hear that a meta-learning can achieve few-shot learning. This is because, with the training tasks, we can find a good algorithm. And a good algorithm can find a good classifier with only a few training examples. So this is the whole framework of meta-learning. If this is the first time you learn meta-learning, it's normal you feel very confused. Let's spend some time comparing the difference between machine learning and meta-learning. So first, let's consider the goal of machine learning and meta-learning. Machine learning is to find a function. For example, you can find a classifier given an image and obtain the classification result. Meta-learning is also trying to find a function, which is denoted as capital F here. And the goal of this capital F are to find a small f. So we have a capital F, which is a learning algorithm, and capital F take training example as input and output a function small f. And hopefully, we can use this small f in the machine learning task, like classification. This is the comparison between the goal of machine learning and meta-learning. Let's take a look at the training data needed in machine learning and meta-learning. In machine learning, you only need training data from one task. You have training examples in a task. Then this is all you need. For meta-learning, you have to collect a set of training tasks. You want to learn an algorithm that can find a binary classifier for you. You have to collect a set of training tasks. You have to collect lots of binary classification tasks. And in each task, you have training examples and testing examples. In each task, you have training examples and testing examples. Because now we have training tasks and training example and testing example. So sometimes they make people very confused. In some literature, people call the training examples support set and testing examples query set. So in a task, we have a support set and a query set. This terminology is widely used. in the approach of learning to compare. Then in machine learning, you have a handcrafted learning algorithm, capital F. Then this handcrafted algorithm takes the training example as input and output the classifier you desire. For meta-learning, you have a set of training tasks. You have many tasks. And with the set of the training task, you learn a learning algorithm, F-phi hat. And because this learning is based on a lot of different tasks, we call it across-task training. To emphasize the difference between meta-learning and machine learning, the training in machine learning is called within-task training in this tutorial. So in meta-learning, we learn from lots of different tasks and have a learning algorithm. This is across-task training. In machine learning, just based on the data dog1 task, we can learn the function. This is within task training in this tutorial. And in machine learning, so with some training example, we find a classifier. Then we use this classifier to classify some testing examples and obtain the classification result. For meta-learning, with a set of training tasks, we can have a learned learning algorithm. Then we need a testing task. This learned learning algorithm takes the training example in the testing task as input and obtains a classifier. This classifier can be applied to the testing example of a testing task and obtain the classification result for the testing task. This testing scenario in the meta-learning is called across-task testing in this tutorial. Because from a set of training tasks, we have a learning algorithm, and we apply this learning algorithm on testing tasks, which is different from the training task. So we call this testing across-task testing. The testing in meta-learning is called across-task testing. In machine learning is called within-task testing. And the interesting part is, in across-task testing, you have to do within-task training. Then you have to do within-task testing. For the loss function in machine learning, the loss is defined over the training example in one task. In meta-learning, we first compute the loss of base on the testing example in one task, and for all the tasks, we do the same thing. Then we summation all the small l. Each task has one small l. We summation over all the small l and have the capital L. And we have to optimize this loss function. To optimize the loss function, you usually need to know how to compute this term. And to compute capital L, you need to know how to compute small l. And this is the procedure of how we compute small l. To compute small l, we need within task training and within task testing. So we need within task training to obtain theta hat based on the learning algorithm we consider. Then we need within task testing to obtain the classification results. So we can compute the loss here. We can compute small l here. So to obtain capital L, we need to know small l. And to obtain small l here, we need a within task training and within task testing. So if your optimization algorithm needs to compute capital L, then to compute capital L, you need within task training and testing. So in across task training, there is within task training and within task testing. So across task training includes within task training and within task testing. In across task training, we have within task training. In a bigger training, we have a smaller training. In the literature of learning to initialize, this across task training is called outer loop. And the within task training is called inner loop. To emphasize that we have some training. In another training, we have a bigger training. And in the bigger training, we need some smaller training. In machine learning, you have one within task training and one within task testing. In meta-learning, we have across task training and across task testing. In across task training, you have to run within task training and within task testing several times. To do across task training, to find the optimal phi. And in across-task testing, you'll have to apply within task training and within task testing. Across-task testing is the same as machine learning. The only difference is, in machine learning, the learning algorithm is handcrafted. And in across-task testing, the learning algorithm is found by across-task training. A within-task training plus within-task testing is called episode. In machine learning, we have one episode. In across-task testing, we also have one episode. In across-task training, we have many episodes. This is the basic introduction to the idea of meta-learning. After the brief introduction I given about meta-learning, let's talk about some specific examples of meta-learning techniques. The first technique I would like to share with you is learning to initialize. And in the family of learning to initialize, the most representative approach, it's model-agnostic meta-learning or MAML. And it sounds very similar to mammals. And this approach is proposed by Chelsea Finn in ICML 2017. I just told you that in meta-learning, there are also 3 steps, as in machine learning. The first step is, what is learnable? So we have to decide what is learnable first. Let's first take a look at gradient descent. In gradient descent, first, you'll have to determine your network architecture. Then you have to initialize the parameter. Then given some training data, you compute the gradient. Then you update your parameter. Then you will update your parameter many times. And finally, you obtain your model theta hat. In MAML, the initial parameters are what we are going to learn. Here, phi is the initial parameters. The initial parameters are what we're going to learn in MAML. For step 2 is just very typical. It's just the same as what I have talked about. So we have a capital L. This is the summation over the small l for all the training tasks. Then we have step 3. We have to do optimization. We already have our phi. We already know that our phi is the initial parameter. We have our loss function, capital L. Then what we only have to do is use gradient descent to optimize phi. And this is across task training. Or it is called the outer loop in the original paper of MAML. To update the parameter of phi, we have to compute the gradient of capital L with respect to phi. To compute this term, what we have to compute is the gradient of small l for each task with respect to phi. Then how to compute the gradient of L with respect to phi? To compute this term, we have to know how to compute partial L, partial phi I. And here, phi I is the I parameter of phi. Then let's see how to compute partial L, partial phi I. So let's first consider the relation between phi and L. So phi is the initial parameter in the learning algorithm. Phi is the initial parameter of a network. So phi will influence the learned model. So if we have different phi I after the gradient descent, the network parameter we finally obtain will be different. So phi I influence all the parameters in theta hat, influence all the parameters in the learned model. Then this learned model will influence the small l we have. We have different theta hat. Then we have different L. So theta hat determine the small l we have. So phi I influence L through theta hat. Based on the training rule. This is something you learn in calculus. Partial phi I, partial L can be formulated like this. U summation over all the parameters in theta hat. And J is the index of one parameter in theta hat. U summation over all the parameters in theta hat. Then you compute partial theta j hat, partial L, times partial phi I, partial theta j hat. Then if you can compute these two terms, you know how to compute this one. Then you can compute this one. Then you can compute this one. Then all the problem is solved. Then let's first take a look at how to compute this term. How to compute partial theta hat j, partial L. This is pretty straightforward. Actually, it is straightforward to compute this term. But you have to know the value of L and theta hat. To know the value of theta hat, you have to do within task training. To obtain theta hat, then to obtain L, you have to do within task testing. And the within task training is called the inner loop in the literature of MAML. However, this within task training can be very computationally intensive. Because as you know, the learning algorithm we use is gradient descent. In gradient descent, usually, you have to update your parameter many times. You have to update your parameter tens of thousands of times to obtain theta hat. So if each time we have to compute the gradient, we have to update the parameter many times, this algorithm meta-learning would be very computationally intensive. To compute the gradient, to obtain phi will be intractable. To deal with this problem, in MAML, what actually do is simplify the learning algorithm. So in MAML, you do not update phi many times to obtain theta hat. You only update phi once to obtain theta hat. So in MAML, the within task training only uses one step. Or to obtain theta hat, what you only have to do is you have phi, then minus phi with the gradient. This epsilon is the learning rate. You'll only update theta hat once to obtain theta hat. So this will largely reduce the computation you need in the within task training. If this is the first time you learn MAML, you may feel very surprised. Because we only update once to obtain the parameter theta hat. Your gradient descent algorithm only updates the parameter once to obtain the network parameter. This is very different from the usual gradient descent. Here, I would like to give you some reason why one-step training is necessary. So the first reason is, as I have mentioned, we think task training will be applied many times in across task training. So once that update, to minimize the computation needed in within task training, is very important. The second reason is, isn't it a good thing to train a model with only one step? Probably with one step update, we can find very powerful initial parameters that only one step is sufficient to achieve the final result. Perhaps with one-step training, phi can be so powerful that only one step can achieve theta hat. The third reason is that meta-learning is often used in a few-shot learning scenario. In a few-shot learning scenario, we have a very limited number of training examples in each test. And when we have only limited training examples, update many times can overfit on the training example. Update only once can prevent overfitting on limited training example. Finally, the fourth reason is, within task training can be different in across task training and across task testing. In a real implementation, within task training is different in across task training and across task testing. In a real implementation, in across task training, within task training, update parameters once. On the other hand, in across task testing, within task training can update parameters many times until the parameters converge. This is because, during the training time, we have to apply within task training many times. We update the parameter once to minimize the effort of computation. But in across task testing, within task training only has to apply once. Because within task training only applies once, you can update the parameter many times. Because you only have to do it once, you only have to apply within task training one time. This makes across task training and across task testing mismatch. However, in real implementation, this trick is helpful. Then let's take a look at this term. So we already talked about this term. Let's take a look at partial phi I. partial theta j hat. If we use a one-step update, the relation between phi and theta hat is simple, is not sophisticated. So this term is actually like this. So I can just write down the formulation of partial phi I, partial theta j hat. In a real implementation, this part, the computation of this part is further reduced. In first-order approximation, we assume that all the terms involving second-order gradients are zero. So this term will become zero. This term will become zero. So partial phi I, partial theta j hat, would be either 0 and 1. So this largely simplifies the computation of this term. So this all about the optimization of mammal. A mammal is not that easy to train. In the paper, How to Train Your Mammal, the author found that mammal is sensitive to hyperparameter. So they trained mammal 3 times with different random seeds. And they found that sometimes mammal can give us the result, but sometimes its performance is poor. So in the paper, How to Train Your Mammal, some tips are used. And the mammal with the tips is mammal++. And they are less sensitive to the hyperparameter. They're less sensitive to the random seed. If you cannot successfully train your mammal, probably you can take a look at this paper to see whether the tips are helpful. In the original mammal, we only learn one set of initial parameters for all the different possible testing tasks. However, one initialization may not fit on all the different tasks. So you can do task conditioning. That is, you give a different task and different initialized parameters. So there are some papers trying to do that, trying to select different initial parameters based on the properties of different tasks. And there are some issues in learn to initialize. In mammal, we try to learn the initialization parameter phi, and this is done by gradient descent. But as you know, if we want to use gradient descent, we have to initialize the parameter. So to use gradient descent to train phi, you'll have to initialize the parameter of phi. You need phi 0 as the initialization of phi. Then this becomes the problem of turtles all the way down. In gradient descent, we need initialization. So now we have mammal, which can learn to initialize. However, mammal still needs initialization. So probably in the future, we need to learn to initialize. Then we will need to learn to initialize. Then we will also need to learn to initialize. And it will be endless. I think this issue is not completely addressed yet. And why mammal is good? There are 2 assumptions. One is the initial parameter learned by mammal can achieve rapid learning. So it is a good initialization. And this initialization can rapidly adapt to all the different tasks. And another possibility is that mammal is good at feature reused. It learns a good representation. So this good representation can be used on all the different tasks. Which one is true? There's a paper. Title, Rapid Learning or Feature Reuse. Towards Understanding the Effectiveness of Mammal. They do a very complete investigation about the reason why mammal is good. Which one is more close to the truth? Based on the paper, the answer is feature reuse. You can check the paper to see the evidence about feature reuse. If mammal tends to do feature reuse, then there is an issue. For example, you'll have a training task, which is binary classification. You want the model to discriminate between apple and orange. You have this training task. Then you learn an algorithm. Then we have a testing task. The testing task is very similar to the training task. We also ask the machine to classify apple and orange. However, we change the label. In the training example, we tell the machine that this is orange. This is apple. This red stuff is orange. This yellow fruit is apple. Then on the testing example, the correct answer given this image should be an orange. The correct classification result of this image should be an apple. If the model simply learned how apple and orange look like in the training task, and it does not really learn how to learn, it does not really learn a better algorithm, then they cannot obtain the correct answer. They will ignore the training example and just say that, oh, based on what we have learned in the training task, this is apple, this is an orange, and this is the wrong answer. Because the training example is different. You have to obtain the classification result based on the training example. So this should be orange. This should be apple, based on the training example. However, if your model does not really learn how to learn, it just learns the knowledge from the training task. It just learns what apple and orange look like. Instead of learning how to learn, it cannot get the correct answer. And this is an issue in MAML. And there's a paper named Meta-Learning Without Memorization. Try to solve this issue. This is all I want to share with you about MAML. There is lots of paper in the family of learning to initialize. I'll put some references in the slides, so you can check them by yourself. Besides learning the initialization parameter, many different components in the learning algorithm are also learnable. Actually, everything in the learning algorithm is learnable. Let's look at more approaches. So in MAML, we already know that we can learn the initialization parameter. And there are other components. In gradient descent, are they also learnable? Yes, they are also learnable. For example, you can learn how to update the parameter. As you know, the most basic form for update the parameter is looked like this. You compute the gradient. You have your model parameter in the last time step. Then the model parameter minus the gradient. Then you update your parameter. This is the most basic form. It does not always give us good results. This lambda is the learning rate. There are many different optimizers. For example, Attograd, RMS prop, NAG, Atom, and so on. Try to provide a better parameter update rule. However, is the optimizer learnable? Is the update rule learnable? Yes, it's learnable. So just follow the 3 steps of meta-learning. Let's take a look at how to learn an optimizer. For step 1, what is learnable? You can formulate the general update rule like this. You have the parameter in the last time step, theta t minus 1. And this parameter is element-wise multiplied by phi prime. And you have gradient g. And this gradient is element-wise multiplied by phi double prime. And this phi prime can be considered as weight decay. As you know, in deep learning, when we apply L1, L2 regularization, in each time you update your parameter, actually you make the parameter smaller and smaller. This is why L2 regularization is called weight decay. This phi prime plays the role of weight decay. For phi double prime is the adaptive learning rate. This phi double prime can be learned from the data. This phi double prime can give different dimensions. Can give different dimensions of the gradient. Different weights. This phi double prime can give different parameters. Different weights. So this phi double prime is the adaptive learning rate. Phi prime and phi double prime are what we are going to learn. The second step is the loss. And there's nothing different from what we have talked about. We have a training task. We have training examples, testing examples. Then based on the training examples, we can compute the gradient. We can update the parameters accordingly. Based on the update rule here. Here phi prime and phi double prime are learnable. They are what we are going to learn in meta-learning. And to compute the loss, we use the update rule here to update the parameter and obtain theta hat. And we can evaluate the performance of theta hat on the testing example and obtain small l. And we take summation over the small loss of all the training tasks. Then we have capital L. Then for optimization, there is something interesting. We can consider this optimization procedure. We can consider the gradient descent as a recurrent network. You can consider the gradient here as the input of the recurrent network. And you can consider the theta here as the hidden state in the recurrent network. And if we consider theta as the hidden state, then you can consider phi prime as the forget gate in LSTM, and phi double prime as the input gate in LSTM. This is your hidden state. And the forget gate determines whether you are going to memorize the information in the hidden state or not. And the input gate determines whether you're going to use the input information or not. And here the gradient is the input information, and input gate determines whether you're going to use this input information or not. But actually, the procedure of gradient descent is not exactly the same as RNN. So what I just talked about is only an approximation. This is because, in a real recurrent network, the hidden state and the input data are independent. But when you do gradient descent, these gradients actually depend on theta. In the literature, people usually ignore the difference. To make the optimization problems here tractable, simply consider gradient descent and the recurrent network, and you can train, say, phi prime and phi double prime as the forget gate and input gate of LSTM. Then you can train the optimizer. And in the paper, Optimization as a Model for Few-Shot Learning, they showed us the result of forget gate and input gate. For the value of forget gate, they found that the value of forget gate is usually close to 1. So it's very similar to weight decay. As you know, in weight decay you usually set the weight as something like 0.9 or 0.99. And the machine also automatically learned that the result of the input gate is not that easy to interpret. You can check the paper for more details. And there's another paper titled, Learning to Learn by Gradient Descent. By gradient descent, they have a very fancy name. This is not a typo. They truly named their paper in this way. Learning to Learn by Gradient Descent. By gradient descent. And they considered the optimizer as an LSTM. They compared the LSTM, which is a learned optimizer, with other optimizers, and found that the learned optimizer, the LSTM, can achieve a better result than other optimizers. You can check the paper for more details. So now we can learn the initial parameters. We can learn the update rules. Then how about network architecture? Can we learn network architecture? Can we consider network architecture as phi? Of course, we can learn network architecture. This is network architecture search. I believe most of you already heard about this technology. There are lots of papers related to network architecture search. And I think I do not have to go through the 3 steps now. You're already very familiar with the 3 steps of meta-learning. So let's just take a look at the optimization part. In network architecture search, now phi is the network architecture. If you can solve this optimization problem, if you can find phi, which can minimize the capital L, then the problem is solved. However, gradient descent cannot be used at here, because capital L is not differentiable with respect to phi. Because now phi is your network architecture. It's something discrete. So now capital L is not differentiable with respect to phi. To solve this problem, reinforcement learning is widely used. You can use reinforcement learning to optimize capital L. The basic idea is like this. You train an agent, and this agent uses a set of actions to determine the network architecture. And phi is the agent's parameter. So we learn the agent's parameters and hope the agent can generate the proper network architecture. And the reward of the agent is negative capital L. The agent will learn to maximize the reward. In other words, minimize the loss function. So we learn the agent's parameter and hope it can generate the network architecture. The network architecture can maximize the reward function or minimize capital L. And this is how you actually do. You have an agent phi, and probably it can be considered as a recurrent network, and this recurrent network generates a hyperparameter of the network architecture. For example, if you want to generate a convolutional neural network, probably recurrent network can tell you the number of filters in each layer, the filter height, filter width, stride of height, stride of width, and so on. Then based on the output of the agent, you have a network. Then you train the network on the training example. And training this network is actually within task training. In the terminology of this tutorial, I know in the NAS, people do not use this terminology. But training this network, training the network, generated from this recurrent network. This recurrent network generates a hyperparameter, and based on the hyperparameter, you have a network. And training this network is actually within task training. Then you evaluate the performance. You evaluate the actual accuracy of this network on some testing data. Then you have the reward. Then you update phi to maximize the reward. And update phi to maximize the reward is actually across task training. In the terminology of this tutorial, this is the basic idea of network architecture search. And besides reinforcement learning, you can also use an evolution algorithm to solve this optimization problem. And besides reinforcement learning and evolution algorithms, you can also try to compute this term. There is an approach called DARTS. DARTS uses some way to make this capital L differentiable with respect to phi. I'm not going to go through the detail here. You can check the paper to see how to make this term differentiable. In image recognition, data augmentation is widely used. You will do some flipping, do some rotation to the image to generate more data, to prevent overfitting. How to augment the data? It's usually by handcrafted rule. You determine how many images will be rotated, and you determine the degree of rotation yourself. But now, data augmentation is learnable. The machine can automatically determine how it is going to augment the data. And I put some references here. And the machine can also learn sample reweighting. So what is sample reweighting? During the training time, sometimes we will give different weights to different training examples. Because you want to weigh some training examples more, and some training examples less. You want your training algorithm to focus on some examples more, some examples less. Then you want to give different training examples different weights. And you need a sample weighting strategy. And it is not easy to design the sample weighting strategy. Different papers can have completely different strategies. For example, for an example close to the boundary, for example, with larger loss, some people will tell you that this example needs larger weight. So your learning algorithm can focus on this especially difficult example. Some people said, this example should have smaller weights. Because this example is close to the boundary. Probably because the label is wrong. The head label is noisy. So you should assign smaller weights to this example, so your learning algorithm will ignore it. So there are different strategies. And it's not easy to determine what is the strategy you're going to use. How about use meta-learning to learn it? How about consider the sample weighting strategy as phi, and use meta-learning to automatically learn phi for you? And people already tried that. And until now, our learning algorithm is still based on gradient descent. We just try to learn the components in gradient descent. How about we just forget gradient descent and replace the whole learning algorithm as a neuron network? Now the parameter of the network is phi. If we can learn this phi, if we can learn this network, then we can consider the machine invents a new learning algorithm. We have a network. This network takes training examples as input and directly output the learned parameter. Then it is not gradient descent anymore. We can consider the machine invents a new learning algorithm. This sounds pretty cool, and people already tried that. Until now, we consider the learning algorithm as a function. And this function takes training examples as input and outputs the parameter. And these parameters take the testing data as input and obtain the classification result. This is what we consider until now. But actually, it is possible to consider learning and classification as a whole. You can consider within training and within testing as a whole. And you can have a function take training data as input, testing data as input, and directly obtain the classification result. The model even does not generate the parameter. It directly outputs the classification result. In the next part of this tutorial, we will tell you how to do that.